Welcome back to our video module on dynamics. Today, I'd like to revisit the cart problem. So, as we recall, we have a cart going to the right, and a while back, we gave it an initial velocity, v0, and we gave it a spring. And that spring was just sticking out from the cart for a while until it hit the wall. And when it hit the wall, the cart stuck to it. And it oscillated back and forth. And the cart has some sort of mass, and the spring had some spring constant. And if you recall, the spring's rest distance was basically the gap between the mass and the wall right as it hit. So we had some rest length L, and we looked at how it oscillated. But what I'd like to do, and so that was the position as a function of time. And I'd like to ask that same question today. What is the position of a function as a function of time? However, today, I'd like to make it more realistic. And to make it more realistic, we're going to introduce damping. As we discussed, in a real system, it doesn't keep oscillating forever. Even on that air track, we could start to see the amplitudes of each oscillation decreasing a little bit. What does that look like? What does the math feel like? That's what we'll explore today. So we'll start off with getting a little bit of an intuition of damping, how it works, and then we'll start to explore the different scenarios of the math. We'll only be able to scratch the surface today, but hopefully it'll lead us on some more interesting material. That said, let's go ahead and add what we're thinking about. We're going to add some sort of dash pot here where you can think of it as a shock, anything that basically opposes motion. And as soon as this cart attaches to the wall, both the spring and the dash pot, these are both going to attach to the wall, and we're wondering what's going to happen. Now, we can already imagine a couple scenarios. One is we can imagine that we're going to chart it. All right, so as time goes by, what is the overall position as a function of time? And we can imagine our original situation was one in which we had a sine wave that went up and down like this, and the amplitude was constant. Well, we'll call it F was, no, that's a bad one. We'll call it A. A was the amplitude. But now we're going to change that, and we're going to say that there's a little bit of damping. So we know that initially that damping is kind of a percentage of the total amplitude. So initially there's going to be a fair degree of damping, and then as it decreases, the damping effect is going to get a little bit less. So it's kind of going to be kind of like this curve right here. And we'll come back to that to try to understand that. So you have something where you have a really, really slight damping. And then another possibility, and maybe we'll draw this in green, or we'll imagine that the damping is really, really powerful. So what it's like you're hooked up almost exclusively to a shock with a really, really gentle spring. And in that case, we can imagine that we might have something that just goes like this. It just, for purposes of illustration, our overdamping curve doesn't follow the example that we have here. What we've done for the overdamping curve is we've started off with some initial displacement in the spring, and we're watching how the spring returns to its resting length. Another way to see it is that the spring is struggling and struggling and struggling to hit its rest length, but the damping is so strong that it never lets it get there. So you don't get the oscillation, because the oscillation happens when the spring overshoots its rest length. Well, in overdamping, it's kept from even getting there. So we don't get to see the oscillations that we can see with underdamped systems. One might also imagine a third option, if one were into these types of things. One might also imagine a third option of a perfect balance. Imagine that you had a shock absorber, you had this device, and you had everything defined, and your goal was that this cart would come to an equilibrium position as quickly as possible. And that might look something like this. So it's as fast as possible. And in fact, this corresponds to 3 scenarios that we can explore as we're looking at this. Right here, we see the biggest term being the biggest influence on motion is the spring. And that is what we call underdamped. And if you were to take a look at this, you could probably make a guess as to the general form of position as a function of time. It looks exactly like our a cosine omega t plus b sine omega t times some sort of exponential. And in fact, that's exactly what you have. You have e to the negative alpha t, some exponential multiplied by our a cosine omega t plus b sine omega t. So really simple, really straightforward. And in a similar way, here we look at this. This looks a lot like just a plain exponential. We're looking at just what the dash pot, just what the damping mechanism does, its influence, and that is going to be x of t equals a e to the alpha t plus b e to the beta t. It's a complex conjugate. B e to the beta t. And the exact forms of this, I don't want you to worry about. We're just trying to feel our way through, kind of like see the basic forms. We're going to get a chance to look into it more in depth in a minute or two. Finally, let's take a look at this. Oh, I'm sorry. And the green one, this is called overdamped. So this is one where the damping overrides, is more significant than the oscillation from the spring. Finally, this is critically damped. This is the perfect balance of the two that gets the system as stable as possible, as quickly as possible. And this one is this equation as a function of time is a little bit different. It's a e to the alpha t plus b t e to the alpha t. Something of that nature. Initially, I said a cosine omega t plus b sine omega t, and that is true. However, once we introduce damping, our original equation of square root of k over m no longer holds. Now, omega is changed by some damping factor. Now, what does that mean? That means that you can imagine you're a particle and you're oscillating back and forth, right? Well, then you get damped. Something's fighting your motion, so your position comes all the way up here. So you're coming up, and then you want to get down here. You want to get down here pretty quickly. But rather than that happening, you get slowed down, which means your x position is slowing down over time. So you can't get back as quickly as you would like to. And in fact, that's what this term introduces. For small damping, of course, you have some small influence. The larger the damping, the larger the influence on the oscillation. And with that, we're pretty much out of time. Join me in our next module as we continue our thinking and explore this a little bit more.